In this video, I'm going to quickly talk about the logic behind making estimation. Particularly, we'll talk about the logic behind making interval estimation. Okay, so just to quickly review that the research question we have is about the population, and in order to answer that, we randomly select a sample. The question is about variables and the relationship between variables in the population. We randomly select a sample, then calculate the sample statistics, for instance, x bar for the sample, which is the mean, and S, the standard deviation, then you make inferences about the population. And we said there are three types of inferences you make about the population from the sample values. The first one is the point estimate, the second one is the interval estimate. So, point estimate is the actual estimate of the population based on the sample value. In the case of quantitative variable, x bar is the point estimate of the population estimate, which is mu. Now, the question is, how can we make interval estimates with some level of confidence? That's what we'll talk about in this particular slide. So, in order to answer this question about how to make interval estimates based on sample statistics, we need to talk about sampling distribution. So, let's imagine that you have a sample size of n and calculated the sample statistic, which is x bar, the standard deviation of S. Now, how can you go from this number to mu, the population parameter? Now, just imagine that you take this sample size, you take a sample of this size thousands of times. Each time you take a sample, you get different X bars. You get different X bars each time you take it. And we have discussed that according to law of large numbers, the average of all these X bars would be equal to the population proportion. And according to central limit theorem, the shape of the distribution of all sample x bars, if you plot them, would be normal if the sample size is big enough. So this is the basics. So what you have now is a sampling distribution of x bars, and the x bar you have for your sample is just one of thousands of x bars that are theoretically part of the sampling distribution of x bars. Now, given the distribution is normal, we can apply the standard deviation rule. According to the standard deviation rule, 95% of observations fall between two standard deviations. So 68, remember that 6%, 95%, and 99.7%. So let's take the two standard deviation value. Okay, so let's talk about the characteristics of the sampling distribution. We know that this sampling distribution is normal, and we know that the center of this distribution is called mu x bar. Mu because it is the mean, x bar because it's the mean of all possible x bars you have taken. And we know that mu x bar is mu, but we actually refer to it as mu x bar. And you also have the standard deviation of this particular sampling distribution, and you represent the the standard deviation as sigma x bar. And we also learned that the sigma x bar is actually equal to the population sigma divided by square root of n, so that the larger the sample you have, the smaller the sampling distribution's standard deviation would be. In other words, the sampling distribution becomes narrower and narrower as you increase the sample size. In which case, I just wanted to understand that the center of this is called mu x, and the standard deviation of the sampling distribution is sigma x bar. And you can calculate the z value specific to any of the samples, including your sample, by using this formula. Zx bar is equal to the x bar, the given sample, minus the center of this distribution, which is mu divided by sigma x bar. Okay, now that we've understood some basics, let's see the logic of how you can make interval estimates from the sample statistics in the next audio bit. Okay, so here is the logic. According to the probability theories and the standard deviation rule, we know that 95% of observations fall between two standard deviations around the mean. Each observation is a sample statistics, x bar. So these x bars have 95% chance to fall between two standard deviations. Another way to say the same thing is that your sample x bar has 95% chance to fall between two standard deviations. Then it follows that how far away your x bar can be from the population mu? Well, two standard deviations either side, right? So how far can your sample value be from the population value? The answer is 2 sigma x bar for 95% chance. Then we can also say that because your sample is 2 standard deviations away from the mu, you can also argue that the population mean is also 2 standard deviations away from the mu. Make sense? So if you're estimating the value of mu based on the sample value, the population value would be anywhere around 2 standard deviations value for a 95% confidence interval. So the logic of this formula, which is confidence interval is equal to x bar plus or minus z times sigma over square root of n, is that we can be 95% confident that the sample, your population mean is is this far away from the sample mean.
Okay, we had just seen the confidence interval formula for quantitative variable x bar. We said that for a given confidence interval, the population mean can be estimated by taking the sample mean and add and subtract to a number, which is basically the margin of error, which is z times the sigma x bar. Z is equivalent to the confidence multiplier, which is 2 if it's 94%, and sigma over square root of n represents the sigma x bar, which is the standard deviation. So this is how you estimate the population values in a range of values. Keep in mind that this formula you're using is basically formula for calculating the z-statistics. And we'll come back to the z-statistic when we actually calculate the same z-statistic in the hypothesis testing. I'll come back to that when we talk about it. Now, for the categorical variable, formula is similar. Just imagine there is a population with a population proportion of p, and imagine that you're taking a sample size of n, and your sample is one of thousands of samples you've collected with a sample size of n. And each time you calculate it, the individual values you get each time will be p hat. So your sample proportion will be p hat. But each time you take a random sample for thousands of times, it would be different. And if you plot all this p hat, just like x bars, and look at the center of the distribution, the center of the distribution would be equal to, its center of the distribution is called sigma p hat, which is the center of all p hats, which is a theoretical distribution called sampling distribution of p hats, which will be equal to the population proportion. And according to the central limit theorem, the distribution of these would be equal to the normal distribution as long as the sample size is large. And we talked about what large is. It is large if n times p and n times 1 minus p is greater than or equal to 10. In any case, the idea here is that this distribution is normal, right? And your p hat is number of standard deviations away, like 2 standard deviations away around the population proportion for a 95% confidence interval, just like the x bars. Just like the confidence interval formula for x bar, the mu was x bar plus or minus z times sigma x bar. This is also same. It's just that instead of x bar, you put the value of p hat, which is p hat plus or minus z times, which is the confidence multiplier, sigma p hat instead of x bar. If the sigma x bar was calculated by sigma over square root of n, sigma p hat is calculated with this formula, which is square root of p times 1 minus p over n. And z p hat, just like sigma p hat, is calculated with this formula, where p hat minus p by sigma p hat. Everything is same, and the logic here applies same as we discussed in the previous slide about the x bar. So again, keep in mind, we'll use this z-statistics for proportions in the hypothesis testing, and we'll use this formula just as we would use z-statistics for x bar. We have a formula that we'll use hypothesis testing.